at what we found for our bell work here. And by what we found, I mean, just have a little brief discussion about this. Overall, looked really, really good. Big thing is going to be remembering to label your axes. Just writing X and Y, because X and Y oftentimes can be very, very arbitrary, is generally a little bit sparse for what we need. So labeling whichever set of data you used for the X's, whether that's hours or ounces of milk, for that particular axis was really important. I saw Nathan, right, did a really good job of, he wrote X and Y for the X and Y axis, but then he made a little key of like X represents this and Y represents that. That's totally fine as well. That's really great, just so long as it's very clear to me, like, okay, what are the X's, what are the Y's, however you want to communicate that is great. Okay, let's take a look at comparing our data that we got. So this is the second part of what we were looking at. And we're the goal for today, or really the first goal for today, is going to be to add some numerical rigor to this process. But I want to start out just kind of super broad, thinking about like descriptors. So we have our correlation, or we have our relationship that has been graphed, and now we're doing the regression part where we're trying to figure out how we can describe that correlation. What do we notice about our bell work example, which is scatterplot 3, compared to the examples that we ran yesterday? Yeah.
Everyone's like more scattered than the first and second. The first one's going up.
Okay, so a couple of really good things here. If we're just comparing our third kind of graph to the first two, the observation that our third one is a lot more scattered is really good. Maybe a good word to use here is there's like this element of randomness that we have for our third graph. And then also the observation that the behaviors of our first two graph, while maybe are somewhat comparable, are also a little bit fundamentally different here. So Ethan, you said as one's going up, one's going down. Let's try to add a little bit of rigor to that. Let's make that like a full statement here. For my first graph, what is happening on average in general to my Y values as X gets bigger and bigger and bigger? So as we move from left to right, what happens to my Y values? They're getting bigger and bigger and bigger as well. So maybe we'll say something along the lines, just to communicate what Ethan was saying, as X is getting bigger, or as X increases, we would say that Y tends to increase, but I'll just go ahead and say Y increases as well. And we see kind of the opposite there for our second example. What happens as X is getting bigger and bigger and bigger as we move from left to right? Y seems to tend to decrease as X increases. Again, always kind of moving from left to right here. Although we could certainly ask the question, what's happening as X is decreasing? And it's doing the opposite, right? For our first one, Y is decreasing for small values of X. For the second one, Y would be getting bigger for smaller values of X. But as X increases, we would say that Y decreases. And this is kind of like the part that we were talking about of we've got this sample. It's not very clean. We don't have numbers that are going to go to it and describe it. But if we're kind of trying to build up descriptors for it, if I told you that we were working with the second set of data, and I told you to predict the relative size of a value of Y for a particularly large value of X, you could say, well, it's probably going to be pretty small. Or if I gave you the first set of data and asked, well, what's going to happen for a particularly large value of X? Well, it might be a good guess, might be that it's going to be a little bit large. For our third example here, if I asked you for a particularly large value of X, does it make a lot of sense for us to guess whether we're going to get a large or a small value of Y? Not really. And that's kind of coming from this randomness element that that Ethan described here, which is that like as X increases, there isn't really a pattern that we see. Certainly not what we might describe as a linear, clear-cut pattern between our x and y. So we might say that like as x increases, y maybe like changes randomly. You can't really use this third plot to make a whole lot of predictions because a particularly large value of x could net you both a large value of y or a small value of y with what looks like similar likelihood. Right? It's about just as likely to get a large value of y for a large value of x as it is to get a small value of y for a large value of x. Okay. Any other observations that we can make? I really like those two. Those are really good, and we'll kind of flesh those out here in a second. But anything else that we can say?
Plot 1 and 2 are still like more uniform than plot 3, they're still kind of spread out.
Okay, so this is a really, really good observation here. So there feels like there is more of a pattern to our first two plots, right? There's something that we can say about this correlation. There's more going on here than maybe what we see with the third plot. Is it perfect? Does it make a perfect line? Does it make a perfect function? Not at all. Could we dedicate the resources to figuring out like a polynomial that passes through every single one of these points? Absolutely, we could. We are not trying to do that. Our goal is not going to be to find an equation that perfectly describes all of the data that we look at that's super complicated and takes every slight nudge in the up or down direction into account. Our goal is going to be a little bit less than that. We are okay with a little bit of imprecision if what it nets us is something that can make pretty good observations. And what we're going to spend a lot of time doing tomorrow is figuring out when is this spread apartness good enough and when is it too much? When is it so spread apart that I can't reliably use it to make predictions? When can I be very, very confident that they are close enough together that my predictions will be okay? Is going to be a lot of what we look at tomorrow. But I think that's a really good observation. What we are dealing with here is messy. We are going to try to impose some order on top of this mess, but it's not going to be perfect. Sometimes it will be, and those are nice times. But for most of what we will work with, it's not going to be perfect. I think that's really good. All right. Anything else? This can just be anything. This is more, I just want to get a sense for like what you guys are looking at, what you guys are focusing on when you're comparing data like this. Nothing to be like particularly rigorous with.
For the third one,
yeah,
the like some of the x's line up together, like they're the same number, but
yeah,
different y's.
Yeah, and in particular, I want to take that and run with it. Do we have maybe I'm trying to think how I would phrase this as a question. So noticing here that there are some x's for which we get multiple y's. If this were like a function that we were trying to connect, we'd run into a problem there. That would break our function. That's an issue. Not so much of an issue for our data collection. It's okay to get different values of y for different x's. It'll affect our results a little bit, but not too horribly. What else do we notice about the x's? I want to focus on the x's for our third plot, because I think there's something interesting there as well. So we've got some repeating y's for some of our values of x's. And do we notice anything in general about the x's for our third plot? It's something I hadn't noticed. My first period and fourth period pointed this out, and I thought it was a really cool observation. Something about the size of most of the x's that we've been given. the numbers are smaller. Most of the x's for this third plot are going to be 5 or less. The vast, vast, vast majority. We only have 2 data points of what happens when x is larger than 5. And so what we have here, we might describe as being like a biased sample. We have a lot more data collection going on from people who are exercising 5 or less hours a day. We don't have that much information about what's going on for people who are exercising 5 or more hours a day. And so maybe the conclusions that we would come to for the group as a whole are muddied up, kind of messed with by the fact that what we are seeing here is not necessarily a nice, clean, random sample, that it does seem to be some kind of bias in the favor of negative x's. I just thought that was kind of an interesting idea to observe, that the spread of our x's is certainly not uniform. There are more x's, this would be maybe left skewed, more small values of x than there are large values of x. Okay, very, very good. Let's put some words to this. So we have described a couple of phenomena that are actually going to be very, very consistent and that are very, very much what we will see across the board for a lot of different correlations here. So for instance, this notion that we pointed out, this idea that as x is increasing, larger values of x seem to tend to give us larger values of y. If that is the case, then we might describe that correlation as being a positive correlation. Conversely, if as x increases, our y is decreasing, we might describe that as a negative correlation. And if there doesn't really seem to be a strong link, if we're not really able to say what's going on for particularly large or particularly small values of x, then at the very least in terms of taking a look at a linear kind of regression, we might say that there is no correlation between these variables. Now, this is not the only way that no correlation can show up. And there are certainly going to be times where being given, where like you will know exactly what the value of y is for a particular value of x, and it can still be no correlation. So one of the ways that we see no correlation is this just random sporadic changing. But we could also have a situation of no correlation where it doesn't matter what x is, our y values are just all the same. There's no correlation between these two variables because changing x doesn't do anything to y. Likewise, we could see a situation where there is no correlation if there's one value of x and all of the y values are the same. This would also be a situation where there is no correlation, where the value of x can net us a whole bunch of different values of y, and there isn't any rhyme or reason to any one of them. So these like kind of perfectly horizontal, perfectly vertical rather, sets of data are also representative of this no correlation. Often though, we will see it as this like randomness, like this sporadic, it could either be large or it could be small, and either way is fine. All right. So what we're going to be looking at, again, at least for the first little bit of today, is what is called the correlation coefficient. Our process of regression we defined yesterday as being an attempt to describe the relationship between our two variables. One of those descriptors is what we have just said about our kind of graphs here, this idea of whether they have a positive correlation or a negative correlation or even no correlation. But there were a total of 3 possible descriptors that we had when we talked about our regression. There's probably more, but the 3 that we are going to focus on. The other element, or the next element, was whether it is a strong correlation or a weak correlation, or somewhere in between. And then the third element was, is it going to be a linear correlation or a nonlinear correlation? Do we have something other than a linear relationship with our data? And the correlation coefficient does actually a pretty impressive job at capturing all of that information in one go. It communicates the strength of the correlation, not alone, but relative to other values of R. It'll communicate whether it's linear or nonlinear, communicates the direction, all in one single value. We just have to be able to look at that value and parse what that is trying to say. So taking a look at our correlation coefficients here. Correlation coefficient, generally referred to with the variable R. What can we observe about the difference between our correlation coefficients here? What do we notice? Okay, so the higher the number, we might describe that as a stronger, ultimately that's what we're working towards, is that we'll have a stronger correlation. What does a stronger correlation look like in terms of our graphic? It's getting thinner, it's maybe less spread apart, maybe a little bit more, well, clustered is again maybe a little bit of a weird word, but I like narrower, I like less spread apart. The word I used in my fourth period was more compact. The data is just a little bit closer together, not as random, not as spread apart. Okay. So as our R gets bigger, we'll say, the data is more compact. And the correlation would be stronger. Okay. Now, is it just as R gets bigger? For instance, how would we compare an R value of 0.5 to the R value that we see of like negative 0.9? Which of those is going to be more compact? Which one would we expect to be showing a stronger correlation? The negative 0.9. Okay, so it's not necessarily just that the R value alone is bigger, but something about the R value as it gets larger, we would expect to see this kind of more compact, but maybe it doesn't necessarily work the same with the positive negative, which means that the whole positive negative thing, if it's not talking about strength, has to be referring to something else. What's the difference between having, in this case, a positive value of R and a negative value of R? What happens if we compare like the R is equal to 0.9 or the? Okay, so if R is negative, then as X increases, what is happening to our Y? It's going down, it's decreasing. What was the word that we used to describe that kind of correlation? The negative correlation. A negative R value gives us a negative correlation. Okay, we can make note of that. So if, and you can write verbally if R is negative. What does it technically mean to be negative? Below 0. So we could also say to communicate R is negative, maybe if R is less than 0, but that literally just is saying if R is negative. Then we have a negative correlation. As we defined above. Conversely, what's going to happen if R is positive? Yeah, we have a positive correlation. To denote positive, I'm going to say when R is greater than 0, but you can write if R is positive, it doesn't matter. If R is greater than 0, then we have a positive correlation as defined above. As X gets larger, in general, the Y will get larger as well. We would expect the y to be getting larger. Okay, so positive and negative doesn't really have anything to do with whether we're clustered or not very clustered. We want to instead, as our R is getting bigger, we want that bigger to refer to the magnitude of R. We want it to refer to the size of R. As our R is getting bigger in both the positive and negative direction, what is it getting further and further away from? 0. Okay, so maybe 0 is going to be like our center point for no correlation. If I want to denote that I'm moving in both the positive and negative direction, and I want that to be treated the same, or maybe a better way, if I want to make it so that it doesn't matter whether my R value is positive or negative, what could I do to R to eliminate the whole is it negative, is it positive thing? Absolute value around R to refer to strength is generally what we're going to do. Just because the strength of R isn't determined by whether it's a positive correlation or a negative correlation, all we're really going to care about is that magnitude getting larger and larger and larger. There's actually a hard cap on what R is able to be, as well as a floor on what R is able to be. Always going to be stuck between -1 and 1. So if R is getting bigger, if R is like close to 1, then we would say that the correlation is getting stronger. The closer we are to 1, the stronger our correlation is. And we might make a note here that as the absolute value of R maybe gets close to 0, the weaker our correlation gets and the more spread apart our data generally is. So for instance, looking at the data sets that we've been analyzing here, what kind of value of R would we predict for our first scatter plot here? So positive or negative, we would say positive. And then would we expect the value of R to be close to 1 or far away from 1? Probably pretty close to 1, right? There's a pretty definite pattern to what we see here. There's not a whole lot of spread. We're fairly well confined. We'd expect a positive number that's relatively close to 1. I like that a lot. For our second scatter plot here, what would we expect? Probably expect a negative value because we are decreasing. And then would we expect to be close to 1 or closer to 0? Probably closer to 1. Again, a pretty clear pattern that almost looks like a line here. Certainly is the case. And then for scatter plot 3, this one might be a little bit tricky, but would we expect positive or negative? Hard to say. It could be either, I would say. When I first looked at this, I thought it might be slightly negative. And we'll compute that. We'll confirm against my suspicions, but I agree it's hard to tell. For this one, whether it's positive or negative. And what would we expect the correlation coefficient to be really close to? Probably pretty close to 0. It doesn't really seem like there's a clear, are we moving up or are we moving down to this? Very good. All right, any questions about our correlation coefficient, the information that we're gaining from it, anything like that? The big pitfall that I want us to avoid is that positive correlation coefficients are stronger or better than negative correlation coefficients. Positive and negative doesn't mean anything about strength. All right, positive and negative just tells us the direction that our data is tending towards. For strength, you look at the absolute value. That's the only thing you care about, right? So a correlation coefficient of -0.9 is better, quote unquote, stronger than a correlation coefficient of positive 0.89. It's similar, but it would be slightly stronger. Feel good? Not too horrible yet? My face. Now we are able to, and what we are going to do here is, we are able to actually calculate this correlation coefficient. We are actually able to put some numerical rigor to it. That's what we're going to do here. Okay. Normally, I really try to avoid giving you guys formulas without explanations. My goal is for this class not to be memorize a bunch of formulas, and that's the lens through which we understand math. I would like us to more be able to like use the understanding of the material to backtrack and be able to figure out the formulas for ourselves. Of course, that is not necessarily always the easiest thing to do, but that is generally speaking my my goal with just math in general. And I was trying to figure out, I actually spent a fair bit of time for this particular formula, trying to figure out how to do that in a way that is satisfying, or that makes things make more sense.
Hey, new hypothesis?
Okay.
It will destroy the old ones before you put on more.
Okay. Destroy them maliciously. Okay, so know that I did try, and we'll take a look at what I might call a more simplified version of this formula and talk about like what each of the parts is doing. But there's a lot of algebra to go from the more simplified quote unquote version to the version that we can actually use. The more simplified version would be great, but you guys don't know what covariance and standard deviation are. So we'll talk very briefly about what those are-ish, and those will become important later. Maybe not covariance, but certainly we'll have a pretty good understanding of standard deviation by the end of this course. But we're just gonna dive on in, and we'll explain it as we go. Okay. Formula for our correlation coefficient. Apologies beforehand. R is equal to. This is going to be n times the sum of x times y minus the sum of x times the sum of y, all divided by the square root of square root in brackets n times the sum of all of our squared x's minus the sum of our x's squared, close brackets, new brackets, times n times the sum of our y's squared minus the sum of our y's all squared. The best of my ability, yes. Okay, a couple of important pieces that we can gain from this. First of all, N is something that is going to show up over and over and over and over again. It's going to be really, really important piece to what we are doing, just in general in statistics. N is what we are going to describe as the sample size of our data set. So N here is our sample size. So if I, for instance, give you 2 data points, N would be 2. If I gave you 70 data points, N would be 70. It's just going to depend on the amount of data that we are using. The rest of this is a little bit tricky to kind of parse through in terms of trying to figure out the like the order in which to do things. But for instance, all of these E-looking things, this is like the sigma notation. So it's asking me to add a bunch of things together. In the case of the sigma xy, it's asking me to multiply all of the x components and the y components. So all of the x pieces of my points and the y pieces together, and then add all of those products together. The sum of the x's times the sum of the y's. Sum of x's is asking me to add all of the x's together. Sum of y's is asking me to add all the y's together, and then we're multiplying those two. And we already know what that is. The sum of the x squareds is asking me to square all of the x components and then add them together. The sum of the x's all squared is asking me to add all of the x's together and then square it. And then similar thing for the y's, sum of all the y's squared, add all the squared y's together, and then the sum of the y's all squared, add all the y's together and then square. Fantastic news for you guys is that our calculator gives us every single one of these pieces. You never have to do this by hand, right? So for instance, let's take a look at our example here. So this was the second example that I had you guys work on in class. So go ahead, re-enter the data that we see for, in this case, absences and grade. This is 6, 2, 15, 9, 12, 5, 8. Delete. And then 82, 86, 43, 74. Once you have all of your data entered, before we were like pulling up the scatter plot and everything, we already know what the scatter plot looks like. You guys are going back to your stat button, and we're going to slide over to the calc button. In this case, we are looking at 2 variables. So we're going to pull up the 2 variable statistics for this particular data set using L1 and L2, and pressing enter a whole bunch of times, you should get a whole bunch of stuff. Whole bunch of stuff. So 2 variable stats, and then enter, 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 should give you a whole list of things. First one that I see is that X bar is equal to 8.14, just so that you know you're on the right page.
I got it.
Note that I am using the grades and absence data set. If you're using the hour and sick time, then you'll get different values. If you press delete over them, it should get rid of them.
Oh, that bar?
Yeah.
Stat. Yeah. Okay. So go to 2. Calculate. Oh, what now?
Very good. See exactly. So I mean.
Yes. If you read here, I'll read it here. That means that someone has been called sleep.
No, we got
Okay. So let's go ahead. Let's go through and fill in the values that we got here. What is the value for n that we see from this data set? So n is equal to 7, which we could have just counted the number of points to get that, but that's fine. What is the sum of the x times the y's? You might have to scroll down a little bit for that one. We're looking for sigma xy. Yep. 3,745. What is the sum of the x's? So it's going to be the sigma x. 57. What is the sum of the y's? $511.
All right, well, I said the first 1, 2, 3 first.
Seven, I got it.
Go to stacks and then to calc.
Yeah, man, you don't got
This is the sum of
Yeah.
the And so we're just filling in that. Okay, on the denominator, we're taking a big square root. We already said we found the value of n. What is that value of n that we found? We said that was 7. What is the sum of all of our x's squared? 579. Okay, and we're subtracting from that the sum of our x's, and then we're squaring that. We already know what the sum of our x's was. That was 57?
Yes.
So 57 squared. Okay. And we're multiplying that by, we're running out of space here, that's fine. We'll just go on down. So n times, what is the sum of all of our y's squared?
38,990.
Very good. And from that, we are subtracting the sum of the y's, but then squaring that. So that would be like 511 squared. Yeah, and you're just plugging that into your calculator and seeing what you get and hoping that you didn't make a mistake with your parentheses. Except no, we're not actually doing that. This works. This is the correct answer. And if you entered everything in and plugged it in, you've done it from scratch. Congratulations. We are going to generate that number in about 10 seconds without needing to plug this in, without needing to do that. In order to do this, you're going to need to go into mode and make sure that your stat diagnostics are on. The default is off. It's towards the bottom. Make sure your stat diagnostics are on. So click mode. Make sure your stat diagnostics are on. We're going back to stat. We're sliding back over to calc. And instead of selecting two variable stats, which we use to compute this by hand, we are instead going to select lin reg. There are two options for lin reg. There's the ax plus b and the a plus bx. It doesn't matter which one you choose. Either one's fine. Make sure our list is all good. You're going to run calculate. And the r value that you see there is this r value. This is equal to negative 0.944. So go to stat, calc, lin reg, enter, 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 And then that R value that you see, if your stat diagnostics are on, should be the R value that we have. Or do you get
Oh,
an
it
R
is
value?
right.
Yeah.
Why? Oh, it is right. I just can't read it.
Yeah, there's an R squared value as well, which actually is even more important than the R value, but we're not going to talk about it in this class. And that's it. That's what you would do. You're never going to calculate this by hand. You're never going to use this formula. This is how you generate the R value. Mostly I was showing you this to generate some gratitude at what you don't have to do in order to do this, since this is what you would have to do it by hand. But we're never going to do it, and so it's fine. So just enter in your data, make sure your stat diagnostics are on, stat, calc, linreg, either one works. R value is what we're getting. Does this R value make a lot of sense when we are considering the second scatter plot that we are comparing to? Does an R value of negative 0.944 make sense for this data? It's negative, so it's going down, and it is close to 1 because it's really, really compact. This makes a lot of sense that we get this kind of R value. Okay, yeah. Let me get you new homes. Take a moment. We are going to take a stab at our third scatter plot data.
Do we do the same thing we just did?
Exact same thing. You don't need to calculate it. You don't need to show work. I'm not asking you to plug into the formula. I'm just asking you, what is the value for? If you go down to, so if you scroll down, all the way down. It'll be on the like side.
To me, it's a loser. It's like the regular. Sad, let's be It's like sad.
I don't know why you're. I'm gonna reset it. Okay, it looks like yours doesn't have it, or I'm not.
I guess should be.
Okay, yeah, I would grab one. Actually, wait. Here's my sheet. Stats.
Wait, do we just have the number?
To me, that's like.
Yeah, you'll go to the third decimal.
So it's gonna be
Numbers.
8. Round up to 2.
Can't put that number.
Okay, so what do you use?
I didn't know.
It's a shooting.
Gosh, I guess one was
They're more ethereal.
Yeah, you'll want to use one.
Alright,
I don't know why that's. Are we able to? Yep, yeah. We good. Perfect. Very nice. Very, very good. And does that make sense with like the data that we saw?
Oh, yes.
Yeah.
I just don't know how to do it.
Oh, yeah, you want to.
Okay.
Remember, this is all about taking the math, doing it on the calculator, not having to worry about it. That is the main. Great. Very nice. Good. Yeah. Yeah.
Or what?
Yeah.
I know.
Yep. Either one. That is fine.
And you're done.
What do you think Mitsuki's music is like?
Okay, told you. Butterfingers.
And it's that.
And
And if the R value doesn't show up, then it's an extra
I'm
number.
getting the wrong one.
You think you're cool? Pass to me
Yeah, so you're going to stats, you're gonna go edit, enter in all the data, and then you would go stats, out. Then
Holy shit.
now, it's not this data, right?
It's like kind of cringe. That's a.
No, I'm looking about it.
Oh my
You
gosh.
can't win, you can't win. I know, I will be nice to you.
You can pick Droppy one on that.
Just no, don't do too much. You win. Just be, don't do too much.
Very nice.
All
All right, very, very good. Very, very nice. What value did we find for our R here?
0.067.
What did we say? Very good. So the R here, 0.067. And does this fit what we saw with our correlation? Yeah, pretty random, not very clustered. We would expect an R value being relatively small, close to 0. And then the fact that it's positive, I think, like we said earlier, it could have been anyone's guess. Who knows whether it would be positive or negative. Interesting thing here is I think without that point in kind of that upper right corner, it's pretty clearly negative. And so it's actually pretty impactful. The addition of a single outlier data point can have a very, very drastic impact on the data and whether we see a correlation or not. Interesting to observe. All right, questions with our correlation coefficients, what they represent, how we find them, things like that. Only trick is really just make sure your stat diagnostics are on. Whenever you reset the calculator, it defaults to off. So you just want to make sure that they are in fact on. How are we feeling? Pretty good? Not too horrible? All right, couple of things to note. A lot of the kind of stuff here at the very, very end mostly is focusing on hypothesis testing, which we haven't talked about yet. We'll introduce that idea tomorrow of what it means to hypothesis test. Main idea being, when is the R value strong enough for us to actually care? And what we're going to see is it depends on the value of n. Among other things. But the last thing that I want to emphasize is the difference between having no correlation and having correlation that is nonlinear. So for instance, scatter plot 3 that we saw here, I would definitely describe as no correlation. Big thing is that that we've got a really wide spread. There's a lot of what we might say is like pretty random kind of assortments of like where the points are, not really great for making predictions. The fact that it had a positive linear regression slope, that the correlation coefficient was positive, was just, how would we even be able to tell that from this data? Very hard to kind of use like this. Let's compare this to a scatter plot like perhaps something like this. Or even better, maybe without all those extremes. If I were to try to run a kind of run this correlation coefficient, run this linear regression on what we see here, what would we expect? Do we have a trend of like as x gets bigger, our y's get bigger? Do we have a trend of as x gets bigger, our y's get smaller? Or do we have randomness? Or do we have something else? We've got something else. It's not quite random, but it certainly doesn't fit the positive negative kind of gist that we constructed earlier. And in fact, if you were to do a linear correlation with this, you'd probably get that there is no correlation. It would tell you an R value that is really, really close to 0. But what we have here really instead is just a more complicated correlation. Right? For instance, if I told you to get me an X value that is relatively close to, say, what we see here in the middle, then you could maybe make the prediction that the Y value is going to be small. If I told you that I gave you an X value all the way out here, then we could maybe make the prediction that the Y value is going to be relatively large. A line just doesn't really do a great job at describing this data, at making predictions about this data. What would maybe be a more appropriate function for the way that this is clustered? What does this seem to really resemble? Yeah, what did you say, Liz?
A parabola.
A parabola. It looks a whole lot like a parabola or a quadratic. And so while a line might not do a particularly good job of describing this, maybe a quadratic would do an even better job, or maybe even a obviously not for this one, a cubic function would be good, or maybe like a quartic function would do a really, really good job. And if we ran the regression for each of those, we would get different values of R telling us how good of a job they actually do. And ultimately, you would select the R value that most closely resembles the data, the one that's closest to 1. We are not going to worry too much about nonlinear regression. I want you to be aware that it is possible. And that there is something very fundamentally different about having no correlation and having a nonlinear correlation. Because if you run a linear regression on something that is nonlinear, it is possible that it will come up that you have no correlation. And that is not really accurate. What you have instead is something that just isn't a line, like what we see. Any questions from 1.1? How are we feeling? Pretty good? Okay. At the start of the class, so yesterday, I guess, I said that our main objective with statistics is to take this really, really messy, not clean, annoying data, to run it through some kind of machinery, and to then make somewhat accurate predictions about the future, or about what's going on prior, or the middle, what have you, using the data that we are given. So ultimately, our goal is to make predictions, to generate something that is good at making predictions. How good those predictions are is also something that we're going to explore tomorrow. It's going to be a little bit related to that value of R. Larger value of R generally means we are happier with our predictions. We are more confident in our predictions. But again, we'll get into that. And what we're going to see with 1.2 is exactly this. We have our data. We've been saying it's kind of behaving like a line. And I say, I agree. Now the question is just what line is it behaving like? Or maybe what line does the best job at taking into account the data that we are seeing here? Number of lines that we could choose from, which one does it best? This line that we are going to be using to make our predictions, to describe our data, is called the regression line. You have likely heard of this instead in the context of it being referred to as the line of best fit. We're not going to get totally deep into all the nitty-gritty of where this kind of term comes from, but the main idea of our line of best fit is the line of best fit. Points on the line represent our guesses. They represent what we would expect our outputs to be matching with certain inputs. And ideally, we would like our guesses to not be too far off from reality. So the line of best fit is not the line that passes through the most number of points on our data. It is also not the line that perfectly fits all of our data. It's not a curve that we're going to be trying to do connect the dots with all of this, anything like that. The line of best fit is going to be the line that minimizes the distance from our data to that line. Or, in layman's terms, that gets as close to as much of the data as it possibly can. So we're trying to really stick close to the data that we are analyzing here, and whatever line does that the best is going to give us the largest value of R, and that line that gives us the largest value of R is going to be what we run with as our guess, as our prediction. So line of best fit minimizes that error that we would expect to see between observation and hypothesis. And we are going to use this to make our predictions. Now we pick whatever line, and by we I mean our calculator, picks whatever line does a really good job of making R as large as possible, the magnitude of R as large as possible. That being said, what we are looking for is a large value of R. The larger R is for a particular linear regression, the closer our data is going to be to the line. The less error we will see between our observation and our guess. So we might say something like the closer the absolute value of R is to 1, the closer our data is to the line. Yeah, grab a pass. Okay. Now, when we're talking about the formula for a line, what is the kind of general equation for a line that everyone knows and has down, all that? Y equals mx plus b is the one that every single person knows. Important things to note. Well, actually, what we're kind of doing is we're saying that a line can be defined through the super annoyingly technical ways, like we have two different parameters on our line. We have the m. What does the m represent? We have the m, which represents the slope, and we have the b that represents the y-intercept. I don't know why, but our formula that we use for a line for our linear regression is not y equals mx plus b, but it's basically the same thing. Instead of saying y equals mx plus b, you will instead see y equals ax plus b, where a is the slope and b is the y-intercept. Or you could also see y is equal to a plus bx, which is the exact same thing as the one above, but the a and the b are just reversed. You'll notice in your calculator, you have two different options for linear regression. One of them uses ax plus b, one of them uses a plus bx. If you run both of them and compare the results, you'll just see the a and the b are switched. Whichever one is attached to the x refers to the slope. Whichever one is not attached to the x does not refer to the slope. It refers to the y-intercept. I prefer to use the y equals ax plus b just because that's the one that shows up first in the calculator, so I don't have to scroll down as far. Pearson prefers the other one because Pearson hates me. I would expect you to be able to understand and interpret both. So on a quiz, either it would be fair game. Like hypothetically on a quiz that we had, like say Friday, you should be able to look at our linear regression that has been run with the ax plus b and one that has been run with the a plus bx and make sense of both of them. Now, just like with our R value, there are some horrible formulas that go with this A and this B. Actually, they're pretty similar to R. It's a lot of like the sum of all the x's squared and the sum of all the x's and y's and the sum, all that fun stuff, and sprinkled throughout there. We're not going to worry about that. Our calculator is going to do that work for us. We're not concerned. As far as just rounding kind of things that I would expect, round to the thousandths place, and that'll be just a pretty good rule of thumb. 3 digits, and you should be fine. Not even scientifically significant digits. I don't care. Just thousandths place should be good. Okay, so how are we going to find this A and this B when we aren't using these horrible formulas? The good news for us is we've actually already found this A and this B. We've already used what we are going to use to find this A and this B. When we were doing the correlation coefficient, when we were doing that lin reg, we were focusing only on the R, but there was also an A and there was also a B, and that is this A and B that we are referring to here. So for instance, taking a look at our first example with the hours worked and sick time, if we go into stat edit, we'll delete all of that, delete all of this. This is 63, 29, 20.8. 18.1. I should, in a couple of days, have access to an application that will allow me to show what I'm entering on the board here so that you don't have to follow, or that you can follow along more closely. But such is life for now, I guess. Entering in the data from this first example. Very riveting stuff. We're going to go to stat. We're going to go to calc. Pick your poison with the lin reg. I'm choosing the ax plus b one, but we just need to be able to interpret what we see. And what I get is that A is equal to 0.106-ish, and that B is equal to 0.396-ish. We could also observe the R. The R here is about 0.982. So pretty strong positive correlation, very strong positive correlation. Okay, I used the AX plus B lin reg. If you use the A plus BX, your A and B are going to be reversed, but that doesn't matter. The formula that you get should be the same. This is going to be Y is equal to 0.106x plus 0.396. And actually what I want you guys to do is enter that equation into your y equals. So y is equal to 0.106x plus 0.396 and go to zoom stat. Zoom stat. And what you should see if you have entered the data is that this line that we have figured out, the equation for which we have determined, does a really good job of staying pretty close to all of our data. Now notice it doesn't intersect any of the points of our data. It doesn't actually touch any of them. It looks like it almost touches the one at the very, very end there. It doesn't. Passes a little bit above it, looks like.
What do you click again to see?
So if you do y equals and then you do zoom stat, it should pull up both your points and both your scatter plot and your the graph of your line. So if you do y equals, enter in this equation. So y equals, enter in the equation that we found, and then do zoom stat. You should get exactly what you see here of the line and the scatter plot.
You said
Zoom stat. So zoom stat. That way you can see it.
And then zoom.
Yours is using, so notice here, this was for like the Bellwether data, because there's no correlation, there's not like. So after,
I did, no, I did.
so, you have the data, okay, so you're gonna go zoom stat. Okay, so this was the data from the
Press zoom and then click 9.
X is.
I did, yeah.
So have you entered all of this data into the stat option? So stat edit, you'll want to enter in all of that data, and then you're going to put this equation, this A value that we get, that B value that we get from doing everything right, into your y equals. Yeah, and that'll be that equation, and then once you have that equation entered, you're going to give a zoom stat, and it'll show the scatter plot and that line. And what we should see is that it does really good. So you have the data entered. Data's all entered. We're going to
I've never even did to
plug into this. Zoom stat will show you how.
I would have stay a lot better.
Back against the wall.
When you write a line or stuff like that, if you
So if you go to y equals, that's where you'll graph like our prediction line.
I was thinking, what's some serious right now?
So we feel good about.
Do we need that line?
If you go to y equals and plug in the line, it'll show you how good of a job our line does it. Yeah.
Please, how do you feel?
So if you do y equals and then put in the equation for the line, you'll want to make sure that basically the Charlie
I didn't tell you.
Yeah.
Banner needs to be on soccer.
Like if I told the time,
You're actually, I didn't do it.
It still works.
the same thing. No, I just, I don't know how to get back. Oh, wait a second.
Why you're not bending them? Why am I going back?
Okay, wait, it might be
Yo, why did that?
Come on, bro, it still works.
You didn't do it right.
That is gone.
Still works.
Plus.
Right, here you go, come on.
Come on, bro, look, let me show you, bro. It still works, see?
Oh.
He's sick with it.
Notice the line is really, really close to all. Doesn't pass through any of them, but does get right into the smallest piece of it.
Chill, why did it fall?
Nope.
You are a child.
It broken.
Okay, not done just yet, guys. As great as that line is, ultimately the goal of generating this line is using it to make predictions. So let us consider our predicting points section here. Notice as well all of the instructions of how you do it. All right, So we are trying to use the equation of the regression line that we found, which was that y is equal to 0.106x plus 0.396. We're trying to use this to say something about the world for various guessed values of x. So for instance, first thing that we are asked to figure out is to predict the amount of sick time that someone will have after they have worked for 20 hours. If they have worked for 20 hours, what are we being given there? Is that an x value or a y value? That is an x value. So here's where it's really, really important to keep track of what are your axes, what are we paying attention to? We have been given an x value here. And so in order to find the corresponding y value, what do I need to do with that x value? Plug it into our equation. Y should be equal to, this is 0.106 times our 20 plus 0.396. Plug that into your calculator. I get that this is about 2.5-ish, 2.5. What does that mean in terms of the context of this problem? What does that 2.5 represent as a y value? Sick time. So we would expect someone who has worked 20 hours to get about 2.5 hours worth of sick time. Okay, we can do the exact same thing going the other direction. For instance, for our second part here, if we are told that we are given that someone has accrued 40 hours of sick time, which is going to be a very large amount. What is the hours of sick time? What does that represent? Sick time is our y. So y should be 40. This is equal to 0.106 times x plus 0.396. What do I have to do to solve for x? Before we divide, we have to subtract from both sides and then divide by that 0.016. So subtracting and then dividing. And I get, so 40 minus 0.396 is going to be 39.6 divided by 0.106. In order to get 40 sick hours, we would expect that someone would have to work about 373.6 hours before being assigned that 40 sick hours. What we are going to focus on tomorrow is how good of a guess is this? Are we happy with this guess? Again, it's going to relate very much to the R value. Should be a much, I'm not going to be trying to squeeze 2 lessons into a single class tomorrow. So you guys should also have a lot of time to work on the Pearson classwork. And so we'll spend a little bit of time on figuring out how good of our guesses are, and then a little bit more doing some of those practice classwork problems. But very good work today. Not lining up before the bell, though. Appreciate you all.
Bro,